But I'm going to be talking about the circular economy of rare earth magnets and telling you why they're important. So I'm going to tell you what they are, where they're used, why they're difficult to recycle, and then I'm going to show you some of the solutions we've been developing at the University of Birmingham. So it's a bit of a complicated slide. If you're talking about rare earth magnets, what you've got to realize is you're talking about a family of materials. At the top there, on the side, they're the percentages of these rare earth materials. The top one, samarium cobalt. It's going to be used more and more in the aerospace industry. You can run that material at high temperature. The rare earth in that material is called samarium. Stepping down, about 95% of rare earth magnets are actually based on an alloy of neodymium, which is the rare earth, iron, which gives you the magnetic strength, and boron, which doesn't really do an awful lot actually in the magnet. And about 95% of the magnets are based on that alloy. What you've got to realize is they're made in lots of different ways, so the supply chains are actually quite complex, and then there's a minor material at the bottom based upon samarium iron nitride. Why is there a lot of publicity around rare earths? Well, they're top of the critical materials list, so they're at highest risk of short supply, deemed by the EU, and most of the material is coming out of China. And if I had more time, I could go into lots of things that have happened around the rare earth market in recent years, including the price volatility for those materials. Now, where are those materials used? Very, very broadly across many, many sectors. It's not just the automotive industry. In the automotive industry, they're used in drive motors, in generators, in power steering units, in loudspeakers, and on and on and on. So there's a lot of this material going into the automotive industry, and that's going to escalate very rapidly over the next few years. It's also used in things like hard disk drives, loudspeakers, in lots of electronics. About 10% now is going into electric bicycles, predominantly in China. Magnetic separators, loads and loads of different applications. And that's one of the reasons why it's tricky to get access to that material and to recycle it. It's been estimated that we import into the EU about 14,000 tons of neodymium iron boron a year. We actually make probably around 1,000 tons in the EU collectively. So we're importing a lot more than we actually make. And it's estimated also that we only recycle less than 1% of rare earths collectively. And that's all of rare earths, not just the ones used in magnets. What are the problems then, if you want to recycle it? Well, first, which of these applications have got neodymium iron boron in them? Some applications, if you took 10 handheld drills, would have different types of magnets, for example. In a mobile phone, you'll have less than 300 milligrams of material. The composition of the magnets changes between application. The oxygen content of the material is higher than primary if you want to recycle them. If you try and shred the materials, which I'll show you in a second, that causes you problems, which is typical in the recycling industry. They're not designed for disassembly. The economics is a bit of a struggle depending on how you do it, so it's got to be very efficient. And the supply chains don't currently exist between the recycling companies feeding that material into the rare earth market. They're just some of the issues. There are quite a few, as you can probably tell. So I've put 3 applications on here just to try and show you some of the issues. On the left-hand side over there, there are 2 sintered magnets in the voice coil assembly. You can see the arrow next to it on the left-hand side. There's between 1 and 25 grams of material in that hard disk drive. If you want to get it out, you need to undo between 10 to 12 security screws. The magnet's superglued in position. It's magnetically attracted to the plates either side, and it's coated with nickel. So how do you get that out extremely efficiently? If you look at the drive motor in the center, this is from a Prius, the magnets are deeply embedded inside the rotor, and then that's got all kinds of casings on top, and you've got to get that off the end of the engine to get to that material, never mind the soft magnets that surround it. In a mobile phone, there's just really small amounts of material, so one of the things that Apple are doing, they're starting to look at robotic disassembly of those products. Why? Well, if you manually tried to separate them, the cost would be too high, and therefore it would be shipped offshore. Just to show you what currently happens to some of these applications, the bottom image on the left-hand side there, that's what happens to hard disk drives if you shred them. The powdered material you can see is the neodymium iron boron magnets. They're extremely brittle. It breaks up to a powder when you shred the electronics, and then it sticks to everything. And that's actually how a lot of electronics are recycled today. They shred everything and then separate the ferrous and non-ferrous components. You can't do that for NdFeB. You'll lose it. And then it's heavily oxidized. Also, if you look at some of the big auto shredders, when you pass motors or transformers through these auto shredders, the actual motor itself, which is imaged on the right, will distort. All the laminations, all the soft magnet laminations will distort, and it's starting to blunt the tools in the shredders. So it's also a problem for some of the soft magnet materials. So that's some of the problems, and I'll be happy to talk about them in more detail later. Are there any solutions? Well, at Birmingham, we've been trying to develop processes to extract these materials, and I'm going to show you a video of some of these processes in a second. Basically, we've been processing these materials in hydrogen, and you may think, well, why on earth have they been doing that? Well, if you take the voice coil assembly out of a hard disk drive, which is the left-hand image at the top there, if you process that material in hydrogen, the magnet will break apart. It actually reacts with the hydrogen very quickly, but it demagnetizes the magnet. So if you put your electronics in hydrogen, you can strip out the magnet material and then separate that from the coating material. You can see the glue tabs, which used to glue it into the device. And because it's demagnetized, it's easier to separate. We've been scaling that into a 300-liter vessel at Birmingham. We can strip out 5 kilos of material already from hard disk drives, but we're also looking at automotive waste. You can see the hard disk drives on the right-hand side in there. We've cut the corner off them, and I'll show you how we do that in a second. There's a porous drum, and essentially this is what happens. So the magnet material reacts with the hydrogen in that vessel. It breaks apart, the coating peels off, and then you can liberate that powder from the electronics, and it shows you how we do that in a second. This is the voice coil assembly, and what we're processing now are actually the cut corners from the hard disk drives. As you tumble the electronics, the powder falls down the conical-shaped part into this collection pot. At that point, the material is air sensitive, and you have to take it into glove boxes. That's how the material is produced during primary production as well. And you end up with this kind of messy powder over here. We can purify that down to parts per million of impurity, and then we can remake that material back into new magnets by short loop recycling it. And we should be doing more and more of that for other applications in the automotive sector as well. So the other issue is, do you really want to manually separate your electronics to get down to the magnet-containing part? The answer is no, because if you did that in the West, it wouldn't be economic to do that. So one of the other things we've looked at are trying to develop new sensor technologies for the recycling industry, and then segregation technologies to separate the component from the waste. So we linked up with a couple of companies in a European project. What you can see on the right-hand side here is a magnetic detector, and it sees the magnetic field above the electronics. That means you can identify where the magnets are in the waste streams. On the left-hand side, a magnetic detector has been built into that sort of dark component at the top there. The hard disk drives are on a conveyor, and that information is then fed into a robotic system which will identify where the magnet is, rotate the waste around, and it will cut the corner off containing the magnet-containing component. That system's currently at Stena in Sweden. It's in a recycling plant. It will process 600,000 drives a year, and it cut the cost enormously to separate that component. Do not underestimate the separation stage. That's where a lot of the cost is for these new applications. It will be the same for batteries as well, by the way, if you want to segregate the components in batteries. So we end up with the cut corners. Goes through that process I've just shown you. On the left-hand side, you get this messy material. It's extremely brittle. If you sieve that material down on a sieve stage, you can separate all the impurities from the waste stream. You get a clean fraction of powder. And then what we've been doing is converting that material into several different forms of magnet, which are listed on the right-hand side here, which if I had more time, I would explain in more detail. But essentially, we've been reprocessing that into sinter magnets, cast alloys, metal injection molded material, and all kinds of new forms of material. Lots of complications in doing that, which again, if I had more time, I would explain. Final slide, I've put a few discussion points up here. Firstly, how can product designers be persuaded to design for recycle? Everyone's designing for maximum performance at the moment, so how do we do that? More information is required on the availability of scrap, so where are all these materials ending up? What properties are required by the end users? If we make a recycled magnet, could you live with the properties that we actually have and the variability? That's a key question for us. Will end users pay a premium for security of supply? So if there are supply issues, and it may happen again for rare earths, will you pay a premium to have access to a raw material in the West? Scale-up is crucial if you want to prove the variability of magnetic performance for these materials, and that's exactly where we're going next. Both primary and secondary materials will be required moving forwards. You can't do all of this with secondary materials. Robotics is likely to have a very big effect on the recycling industry, in my opinion, just simply due to the complexity of new products coming down the pipeline. Short loop recycling, we should look at that for all kinds of products. Can we short loop recycle materials and then also reuse the components? And the Western rare earth supply chain, you should be aware, is, in my opinion, it's a critical juncture. That supply chain is very narrow now in the West. There are some key companies which we should be supporting in the West. Otherwise, you will lose that expertise in the West today. Hopefully, I'm roughly on time, so I'll stop there.